Assalamualaikum warahmatullahi wabarakatuh. We are from Group 6 and we are going to present our project entitled Chemistry in Perfume Molecular Symphony, The Secret Behind Scents. My name is Amni Inshira binti Maskuri, number matric AN250125.
Hi, my name is Justin Raj and my matrix number is AN250196.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Dini Syakal bin Abdul Muiz and my matrix number is AN250041.
Assalamualaikum warahmatullahi wabarakatuh, and hi to my lecturer and my friends. I will introduce myself. So my name is Nur Syafina binti Omar. My number matric is AN250089.
Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Putra Alexander Kibero Hizam and my matric number is AN250223.
This flowchart shows the project planning process for our topic, Chemistry in Perfume. First, we selected the project topic and identified the main objective, which were to study the chemical components in perfumes, understand fragrance volatility, and relate perfume to engineering chemistry concepts. Next, we conducted a literature review using books, journals, and reliable online sources. Based on the information collected, we analyzed important chemistry concepts such as organic chemistry, chemical bonding, and chemical kinetics. We then related this concept to daily life by explaining perfume notes, skin interactions, and fragrance performance. After that, we evaluated the benefits, applications, and disadvantages of perfumes. The findings were compiled into a project report, followed by a review and editing process to improve the quality of the report. After completing the report, we prepared and recorded a video slide presentation to communicate our finding effectively. Finally, both our report and video presentation were submitted as final project deliverables.
So, I would like to start with something that I think almost everyone in this room can relate to. We have all had those chaotic mornings where we are sprinting across campus or packed onto a crowded shuttle bus trying to make it to a lecture hall on time. And usually, a quick spritz of perfume or cologne is our absolute lifesaver. It's like this invisible armor that gives us an instant confidence boost before we step into a room full of people. But as an engineering technology student, we wanted to look past the beautiful glass bottles and the fancy marketing. The reality is that a bottle of perfume is actually a highly sophisticated, engineered chemical delivery system. The whole process of making a fragrance perfectly matches that famous line from our syllabus: chemistry is just like cooking, but don't lick the spoon. By tweaking molecular weights, covalent bonds, and functional groups, chemists can control exactly how these volatile molecules evaporate on our skin and move through the air. So, our goal here is to take those abstract formulas from our textbooks and show how they actually work in our everyday routines. Next, that will bring us to the actual problem we wanted to solve with this study. Even though we all use fragrance constantly, most people have no idea what's actually happening on a molecular level. We tend to think things like, why does this perfume fade after an hour? Or, why does this smell different on my friend than on me? Are just random arbitrary quirks of the product. But they aren't. They are completely predictable chemical phenomena. On top of that, dealing with synthetic organic compounds brings up some really complex questions about chemical formulations, structure, and safety analysis. To make sense of all of this, our group focused on three main objectives. First, we want to look at commercial perfumes and break down their primary chemical components and functional groups. Second, we are going to investigate molecular volatility, basically studying the timeline of how different scent notes evaporate over time. And finally, we want to connect all of this back to core engineering chemistry principles, specifically looking at how the system behave when they are in a solution. Ultimately, this project lets us map out the entire life cycle of a scent, from that sharp burst of citrus you smell when you first walk into a morning class to those heavy base notes that are still clinging to your clothes by the time you get back to your room at night.
So, before we look at the three tiers of scent notes, let's establish the three physical pillars that control scent volatility. First, we have vapor pressure. This determines how easily a liquid organic molecule escapes into its gaseous form, so our noses can detect it. High vapor pressure means fast evaporation. Second is molecular weight. Smaller, lighter molecules have higher kinetic freedom and fly into the air quickly, while heavier, larger molecules remain anchored to surfaces. And then lastly, we look at molecular polarity. The stronger attraction between molecules, such as dipole-dipole interactions or hydrogen bonding, the more they cling to each other and your skin systematically dragging down their evaporation rate. Now, let's start with top notes. This is the immediate scent you detect right after spraying. Physically, these compounds have a low molecular weight, typically around 150 grams per mole, and very high vapor pressure. Classic examples include monoterpenes like limonene, which give citrus fruit their bright punch, and linalool, which defines lavender. Because these molecules have small size and short hydrocarbon structures, they exhibit incredibly weak intermolecular forces. Dominated almost entirely by weak London dispersion forces, consequently, they require very little ambient thermal energy to overcome these weak attractions. They transition from liquid to gas almost instantly, delivering a sharp, vibrant, but transient impact that only lasts for the first 5 minutes to 15 minutes. Now, we talk about middle notes. As the highly volatile top notes fully dissipate, the middle notes, also known as the heart or signature body of perfumes, begin to emerge. These are typically floral, fruit or spice aromatic like geraniol from roses or eugenol from clove. Physically, heart note molecules possess moderate molecular weights ranging between 150 to 200 grams per mole, giving them intermediate volatility. But here is the chemical trick. These molecules frequently feature polar functional groups such as hydroxyl and aldehyde groups. The highly electronegative oxygen atoms in these groups allow the molecules to form intermolecular hydrogen bonds and strong dipole-dipole interaction with both the solver matrix and your skin. These act as molecular brake, significantly reducing their vapor pressure and slowing down their evaporation rate, allowing the core fragrance to remain stable for 2 to 4 hours. Finally, we reach the foundation, which is base notes. These are the chemical anchors of the perfume, providing profound longevity. They are deep, heavy scents like vanillin, muscone, or coumarin. These compounds have high molecular weights, typically over 200 grams per mole, and extremely low vapor pressure, making them highly non-volatile. Structurally, they feature massive, intricate geometries like multi-substitute benzene rings or microcyclic hydrocarbon chains. Because of their large, highly polarizable electron clouds, they generate incredibly strong and dense London dispersion forces. These forces allow them to bind tightly with one another and with natural lipids on human skin. This massive intermolecular attraction prevents rapid vaporization, systematically regulating the overall kinetics of the scent release. This is why you can still smell a warm vanilla and deep musk on your clothes 6 hours or even days later. This brings us to fascinating question. Why does the same perfume smell different on different people? It comes down to the surface chemistry of our skin. First, thermodynamics. Individuals with a higher metabolic rate or warmer body temperature supply more kinetic thermal energy to liquid perfume. This accelerates the breaking with van der Waals bonds, causing the top notes to flash off much more aggressively. Second, we have liquid solubility, governed by the rules light dissolve light. Oily skin is rich in sebum, which consists of hydrophobic fatty acid. These lipids dissolve non-polar perfume compounds exceptionally well, holding them back and resisting evaporation. On dry skin, these molecules escape much faster. Lastly, skin pH. Our skin is naturally slightly acidic, hovering between 4.7 to 5.75. Minor individual fluctuation in skin pH can cause partial protonation or deprotonation of specific organic functional groups. This subtly alters this geometric configuration of the scent molecules right before they reach your nose, creating a unique olfactory signature for every individual.
On this slide, I will explain how molecular interaction affect perfume performances. Perfume contains fragrance compounds dissolved in ethanol, and the attraction between molecules influences how the perfume behaves. From the table, we can know that weak intermolecular forces such as London dispersion causes molecules to evaporate quickly and create the top notes, while moderate dipole-dipole interaction contribute to middle notes, while the strong hydrogen bonding produces long-lasting base notes. Therefore, intermolecular forces determine the volatility, diffusion, and longevity of the perfume. Well, for this slide explains the role of chemical kinetic in perfume. After perfume is applied, ethanol evaporates first and releases fragrance molecule into the air. Different compounds evaporate at different rates, forming top notes, middle notes, and base notes. Factors such as temperature, humidity, and air circulation affect the evaporation process. Higher temperature increases molecular energy, causing the perfume to evaporate faster and reducing its lasting effect. So, from the picture attached, we can see how molecular energy affected under different temperature. This concept can be also expressed through the Arrhenius equation. So well, for this slide, I will explain the chemical composition of perfume, also known as the involvement of organic chemistry in perfume. Perfume are mainly made of organic compounds such as alcohol, esters, aldehyde, ketones, and terpenes. Ethanol acts as solvent, while compounds like ester provide fruity and floral scents. Aldehyde and ketones add freshness and complexity to the fragrance. By combining these compounds in suitable proportion, perfume can produce unique, stable, and long-lasting perfumes. So from the table, we can know that ethyl ethanoate from the functional group of ester give us fruity scent, and benzyl acetate from the same functional group ester give us jasmine scent, and decanyl gives us citrus scent, limonene from terpene group give us lemon scent, and linol from alcohol group give us floral scent. So well,
For the benefit parts of the perfume is, first benefit of perfume is that it produces a pleasant scent. When ethanol evaporates, fragrance molecules are released into the air and create aroma that we smell. This process is assisted by London dispersion force, which help the fragrance spread effectively through the surrounding environment. The second benefit is that perfume can last for a long time on the skin. Perfume with stronger intermolecular force evaporates more slowly, allowing the fragrance to remain detectable for a longer period. Factors such as molecular size, temperature, and intermolecular force influence the evaporation rate. Therefore, notes such as sandalwood and musk tend to last longer compared to lighter fragrance notes. The final benefit is the wide variety of scent available in perfumes. Most perfumes use synthetic fragrance compounds because they are more cost-effective while maintaining a scent similar to natural ingredient. These compounds are produced through organic synthesis, which provides greater consistency and stability. Different organic functional groups create different aroma, allowing manufacturers to produce diverse range of fragrance. For the application part, the first application of fragrance compound is in personal fragrance products. Examples include perfume, eau de perfume, eau de toilette, body mist, and colognes. These products are used to create a pleasant scent and enhance personal confidence. They contain organic compounds such as ester, alcohols, aldehydes, and terpenes, which contribute to their unique and distinctive fragrance. The second application is aromatherapy. Aromatherapy uses essential oil to promote relaxation, reduce stress, and improve overall well-being. Fragrance molecules such as linalool, menthol, and citral are detected by olfactory receptors in the nose. Their effectiveness depends on how quickly the molecule evaporates and reaches this receptor. The third application is in air freshener and cleaning product. This product use fragrance compounds to eliminate unpleasant odors and create a fresh environment. Their effectiveness is influenced by intermolecular force and evaporation rate, which help the fragrance disperse through the air and maintain freshness over time. For the disadvantage part, first disadvantage of perfume is that they may cause skin irritation or allergic reaction in sensitive individuals. Some perfume ingredient can be absorbed through the skin and trigger allergic response. Organic compounds such as alcohol, aldehydes, ester and synthetic fragrance molecule may act as allergens, causing symptoms such as itching, redness and swelling. The second disadvantage is air pollution. Perfume release volatile organic compounds or VOC into the atmosphere. These compounds can react with other pollutants and contribute to the formation of ground-level ozone and fine particulate matter known as PM2.5. As a result, they may pose health risks, particularly in the densely populated urban areas. The third disadvantage is that perfume production involves the use of potentially hazardous chemicals. Compounds such as alcohol, ester, aldehydes and ketones must be handled carefully during manufacturing. Proper control of reaction condition is essential to ensure product quality, improve production efficiency and minimize safety and environmental risks.
So I will conclude the overall of our topic perfume. So the perfume formulation beautifully applies core chemical principle to daily life, such as organic chemistry shapes unique scents through molecular structure like ester and aldehydes. Chemical bonding, which is intermolecular forces, detectors fragrance longevity, and chemical kinetic drive the transition of scents over time, creating distinct top, middle and base note through varying evaporation rates. Together, the scientific forces drive innovation in the modern fragrance industry. Overall, the chemistry behind perfume demonstrates the practical application of scientific principles in daily life while providing a deeper understanding of how chemistry contributes to the development of modern consumer products. Furthermore, future improvements and innovations in perfume formulation could focus on the use of sustainable ingredients, advanced encapsulation technologies, and enhanced molecular design to produce longer-lasting, environmentally friendly, and high-quality fragrance that better meet consumers.